Hey AP Calc students, this is Melody with her Ghetto Notes again. Right now we're going to be covering the y-axis and shells versus washers and when you should use them both, and I'll probably have another video under this with examples. In the video above it will probably be the x-axis. Alright, so let's start out with washers. So we're going to draw our little coordinate plane, and since I'm videotaping this and doing this, I'm going to have to put my phone down for a little bit. Going around the y-axis. So let's say we have two functions. This function is g of y, and this is h of y. And this is our little rectangle. Alright, so a few things going on here. We're going around the y-axis. So this little rectangle is going to flip around and make this kind of like washer going this way as opposed to this way when we were doing the x-axis. So notice how we're in terms of y because we're doing washers, and whenever you have washers around the y-axis, your functions are going to be in terms of y. So the equation for this would be v equals pi from c to d over here, parentheses h of y squared minus g of y squared again, all of that times d of y. Alright, so now we're going to move on to shells, and then we'll talk about the differences between the two. Okay, so unlike washers, shells, when you're around the y-axis right here, you're expressing the function in terms of x, and you're going to integrate from a to b, and whenever we use a to b for integration, it's always on the x-axis as opposed to c to d. So we're going to have this function, and here's our little rectangle. And notice also how when we're doing washers on the y-axis, our rectangle is going this way because, I don't know, that's just how it is, I guess. Math is like that. But then when we're doing shells, our rectangle is going up and down. Cresswell probably has better insight as to why that is. But when I was learning that, he didn't really explain that as well as I would have liked. So that's why I wanted to just point that out, because that's really important. Okay, so this length right here, to the middle of that, sorry, that's really good, is x, and then this is d of x. And so the equation would be 2 pi from a to b of x times the function in terms of x dx. So that way is really simple, but it's a little bit harder to understand for some people, so I'll explain it in a different way, like I did the last time. Okay, let me draw this really quick. So let's say our function is going down. We're still from a to b. Here's our rectangle. Okay, so this right here, this little width, is going to be the change in x. And this height is going to be h of x. And then from here, it's going to be p of x. It's easier to see when you're doing an example, and I'll do an example of that, but that's basically the model for shells on the y-axis. And that gives more detail as to like what the, width is right here, and just how big the gap is going to be and the height and everything. So the equation would be volume equals 2 pi from A to B times P of X, oh my gosh, my paper's moving, times H of X dx. Alright, so some things to point out. When you're doing washers, remember that when you're integrating, it's from C to D on the y-axis when we're going around the y-axis. So when you're doing washers, if it's on the y-axis, you're integrating on the y-axis. And if it's on the x-axis, you're integrating from A to B on the x-axis. It's y-axis, so our functions are in terms of y, and it's pretty simple to understand. But shells is a little bit trickier. Shells, if we're going around the y-axis, we're doing A to B on the x-axis, and our equations are in terms of x. I should probably write f of x. And same example down here. So thanks guys for watching my little ghetto video. I'll do another video about examples and more differences between them, and give you a little bit of insight as to why these work a little bit better. Thanks guys.